When you have a given antenna as such, doesn't matter what kind of antenna, all antennas have two things. They have the directivity or gain, I use directivity, that is defined, and they have the actual internal impedance of the antenna. These are two things they always have, okay? Just the reality. Now, when you take a look at this, and you want to get a complete circuit for this, you assume there's a certain power density that's incident on that antenna, and you want to know how much power is received, right? We've done this already. But the amount of power received, this is power in watts by the antenna, would be the aperture of the antenna times the actually incoming power density that's normal to the antenna surface. And that aperture is lambda squared over 4 pi times the directivity of the antenna. Remember, that is a function of angle times the power density. And this is in watts. Do y'all remember that class? We've done this. Lambda squared over 4 pi times directivity is really the aperture times the average power density is the amount of power received. But that's not the amount of power developed at a load. So what they do to talk about this is, well, where did this come from? Without getting into the proof, where it came from is this. They assume, you can write this down, that the antenna is hooked into a matched load. So we can say matched. Where this impedance value is actually Z antenna conjugated. Now the reason it's the conjugate is because when current flows, it has to flow through the antenna impedance and the load impedance. The conjugation gets rid of the imaginary component. So that means the total circuit of this antenna would actually look like this antenna with all that power being received. And then you've got an antenna impedance. And then you have Z antenna conjugated here. And I know all that power is being received. That's how much power is received. I put it down there. Are you with me? I'm going to do something at this point, and I'll finish this. I'm going to say that Z antenna will just be equal to R antenna, or we'll call it R rad, the radiation resistance of the antenna, and that will be equal to R load. Now that means the current I flows through there. Does this make sense to everybody? Right? You're receiving that much power. I'm not showing you the voltage source creating it. That much power has got to be dissipated by these loads. The Greek class. There's an internal and an external. So how much power is it? I did that for a reason. I can say, well, if I look at that, the P received, that's the total power, would be equal to 1/2 I, or 1/2 the current, I can do it this way, 1/2 V naught squared, or V open circuit squared, because Wentworth's book says V open circuit squared, divided by the total impedance. In this case, the imaginary parts cancel, and I'm just going to have 2 times R radiation here. Now if you can take a look, it's 1/2 V squared, V open circuit squared, and this would be where V open circuit would be developed at that point, the differential. So I want to calculate V open circuit, and I can see I get V open circuit equal to the square root of 4R rad times the power received. This is my last point with this. The whole thing about this is that the amount of power you receive, the most you can get out of that onto a load is 1/2. And that's if the load is the conjugate of the antenna impedance at that frequency. If you have any other load, it'll be less than that. So the classic problem is, now, or what happens is we replace this, once we know the parameters of the antenna, by just an open circuit voltage. And that is the peak voltage given by this. This is in his book. And then we can remove this load and put any load we want on and calculate the current. Y'all with me? Then it's basically what? A circuits problem. You got two elements. You need the current or power or voltage. You can figure it out. All right, thank you for hanging in there. I owe you 5 minutes. I'll figure out a way to make it.